All right, so before we dive back to the course material, quick reminder, your assignment number 1 is not due this week, but it will be due pretty soon. But anyway, please check the deadline. But if you got any trouble doing the task, let me know, or you can reach out to TA either way. But I'm more than happy to help during my office hour. And guys, please notice this problem here, extended one, all right, split array harder. I think that one there will help you on your programming test, if that can give you a little bit more motivation, all right? It's a very nice one to try. It can really kind of reaffirm your recursive thinking and also to see how you can use the, for example, the array list library class, right? So dive into it, struggle with it, and let me know if you got any trouble. I think the actual solution, I will delay that a little bit, and then maybe you guys can give it a try, talk to me, share any insights you might have, and then at some point I'm gonna give you the solution. Hopefully, if I can, I'll try. If I can maybe give you any kind of like a video walkthrough about the solution, I will try. But at least I'll give you the solution code, at least. Okay, I'll see what I can do. And office hour, no change, all right? And for the contact information for the TA, they are ready if you want to reach out for help. Any course material other than assignment, you may want to reach out to me instead. TA may not know that much, right, about the policy, etc. All right, if no question, let's do a quick recap. So last time, we basically started talking about different terminology, right? I'll just name them very quickly, right? But you got to dive into the definition. We talk about computational problem. Accordingly, you will have some algorithm. According to the problem, there should be some well-formed input and also expected output. Inside the algorithm, you will have just a list of steps manipulating the data structure, which we're learning for this course, of course. And then, in order to judge how good your algorithm is, you got to look at two things, correctness and also efficiency. And correctness should really come first. And we talk mainly about just for you to do testing. We don't really cover any testing strategy in the course per se, but I would suggest you guys practice writing JUnit test cases in your assignments and even in your programming test. It's really going to lead you a long way. Efficiency, and we're going to focus more on the time perspective, which we're going to continue in the lecture today. And for the space, not too much, but just bear in mind, space is also an important factor. It might also impact the running time performance, like the repeat algorithm that we did, right, about the experiments. So today, we're going to more move into the mathematical function approach as opposed to experiments. And don't forget, you got to review about what's the limitation for experiments. That's really the very reason that we are moving from experiments into mathematical function, big O, which we're going to touch very heavily today. All right, and then that's the experiments. You guys can take a look and just to get more intuition. And we'll talk about counting the primitive operation. This one here just about attribute access using dot notation. We assume that it's always going to be constant. It's not going to depend on the input size. And also we talk about method call in general. For now, I was trying to be a little bit vague. It might cause some confusion, right? So I would suggest, for now, just understand the following. Whenever you're making a method call, until you actually do some deep analysis about that particular method being called, you can never say it's a primitive operation or otherwise directly. You have to analyze it, right? That's really the main point. And we're going to see different cases or different shape of the loop, which is going to cause different results when we do analysis. We'll see more. So I would say just keep this page here more like an intuition, right? For method call, you have to do thorough analysis before you can determine whether that should be primitive or not primitive. And we did this example here thoroughly last time, right? I may not repeat again, but I want to draw your attention quickly. Whenever you're seeing something similar to this, so here are the aspects you want to watch out for. Number one, you want to figure out for the loop header exactly how many primitive operations are involved and also how many times they will be executed. And also for the body of the loop, how many times exactly it will be executed. Not today, but on Thursday, I'm going to give you guys I'm going to go over with you another example where we got nested loop. We'll see two examples about nested loop. Right? We'll see how exactly we can analyze it. But please make sure you study this example here pretty well, thoroughly. Right? And you can just review these two questions here, and the answer you will get, which I didn't write very properly on the page. But if you look at the slides, the bullet point here shows exactly the detailed breakdown of the primitive operation. And the final answer will be 7n minus 2. Just a little bit look ahead about what you might be given in the written test or the exam. For this kind of piece of code that you're given, there might be two possible things I can ask you. Number one, count the precise number of primitive operations, which is like this one. If you got the answer, for example, 7n minus 1, wrong. You might get some partial mark, but just wrong, because I want the precise number. What we're going to see either towards the end of today or more likely on Thursday. Given the same piece of code, sometimes what you're asked to do may be just to approximate the running time, which in which case counting the precise number of primitive operation may not be necessary, right? So these are the two different scenarios. I want you guys to master both. Both are important, all right? All right, so that's the one we went over last time. And then, so let's move on to today, okay? No question, hopefully, all right? All right, so one thing I want to draw your attention to, the next slide, slide number 15. So this is just a very similar example here. Rather than using for loop, we're just using while loop. And this one here will be left as exercise for you, okay? Somehow I forgot to put the answer on the slide. I will do that a little bit later today, or maybe soon after I release the lecture recording. Give a try on this one. This one should be rather easy to complete in a very similar fashion, okay? So this will be exercise for you. So I'm going to leave this page over here clean. You guys can try, print it out, and do kind of the same kind of analysis as we did last time. So I'll put it here, exercise for you. And the same kind of questions you may want to answer first before you actually start counting precisely the number of primitive operations. And as I said, I will give you the solution very soon. Okay, but of course, if you got any trouble, even to invert or to count, let me know. Okay, so we can save more time for other stuff. All right. All right, this page here that we're going to start right away is very, very crucial, right? So what we want to do now is going from experiments into relative running time. So we don't want to calculate even the precise primitive operations in most scenarios, but you guys should still know how to calculate the precise ones. So let's see how we can go from absolute running time into relative running time, right? So that will be very important transition we have to make. Let's start with some bullet point here, okay? So each primitive operation by definition, they will take some constant amount of time to execute depending on the platform. Well, I'll give you some concrete example. And let's say this. Let's say we have some variable t over here. Okay, I'll start building something from scratch to go with you. It's a very important transition for us to make. So our goal is to say, if you want to compare different algorithms and you want to choose the most efficient one, how are you supposed to do it? We're going to argue that at the end, rather than comparing their absolute running time, like for example, how many milliseconds exactly, what we can do is we can just calculate their relative running time without worrying about the underlying execution environments. Either it's a Mac or Windows. We shouldn't really need to care. So what I will start with is, let's say we assume we have a variable here called t, little t, okay? So let's say this t over here is, by definition, the exact amount of time that will be taken to execute a primitive operation in some execution environments. Okay, let's consider some hypothetical example right away, just for you to get a feel. Okay, let's say I'm talking about Mac, right? Just Macintosh computers. Let's say this may not be the newest model. So let's say we got a Mac, let's say M1. In which case, maybe each primitive operation will take maybe 2 milliseconds, let's say. And then I may got another one. Let's say the Mac I'm using here is back in 2014, pretty old. So presumably it will be slower. 14, and then the t over here will be a little bit larger. Let's say 4, okay? So that's really what t means, right? Sound time. And we're going to see how we can use the t to really calculate the absolute time. Let's see how exactly that will work first. And then we can see how we can safely drop t. That will be the flow. All right. So let's now talk about algorithm. So let me just use a table to kind of, I think a table might help the most. Okay. Let's say, okay, let me draw it here. Okay. Let's have a table here. And then, just bear with me. Okay, a table here. And the platform we're considering is Mac, let's say M1, right? That's this one here. And the second one is the Mac 2014 version, right? So these are the two different platforms. Let's say we're considering two different algorithms. The one we spoke about last time, right, the find max, that one there is like a 7n minus 2. And the n over here, of course, the input size, right? Okay, let me just make sure I write a little bit better. So think about the n over here is the input size. So in the case where n is equal to 10, it will be 7 times 10 minus 2, we got 68. In the case of the n being equal to 100, we got 7 times 100 minus 2, which would be 698, right? Etc. Right? Let's say we got another algorithm to compare. That one there, we got, let's say, somehow hypothetical 10n plus 3. Right? Just a different like a function that we come up with by calculating the precise number of primitive operations. And then, how do we calculate a precise running time, right? So what we want to do is, so here, we'll talk about the absolute running time that we're going to calculate over here, all right? How exactly, all right? Let's say for the Mac M1, because we know that it's going to be 2, right? So we first of all got to figure out exactly how many primitive operations there are and calculate that and then multiply by the number of time, the amount of time it's going to take for each one of them, right? So I'm going to write down here. So for the first one, it's going to be 100 multiplied by 7 minus 2 times 2, right? So here we're assuming that, assume n equals 100, right? Just for simplicity, okay? Let's see. All right, so that's why you see 100 here. That's the input size. And this guy here is the t for that particular execution environments. All right. And then let's say, what about for the same algorithm, just for the same one? If we want to execute it in M1 versus executing it in 2014. That one there is going to be, let's say, still the same formula for the primitive operation. I still got this, right? That's 7n minus 2. But now I'm going to say multiply by this 4 here, right? Because it's going to be slower in the older model. So also good? And now I want to compare, let's say for the same algorithm being executed in two different environments. Is the absolute time over here the determining factor for me to decide which one is more efficient? Not really, because you can see it's just a multiplicative constant over here. Multiply by 2, multiply by 4, doesn't really matter, right? I just need to somehow know that for this particular algorithm, how long it's going to take, right? I don't really compare one algorithm with itself normally. I only compare algorithm with another algorithm, okay? Okay, so here, this will be one angle to consider. For the same algorithm, we don't really need to worry too much about what t is, because it's the same algorithm. For the same algorithm, t is not very useful, because we are supposed to compare that with another algorithm. Another algorithm. Okay? That's point number 1. All right? Let's get to the more interesting aspect here. Let's say we got some competitor. We want to choose between either this or this. Which one should we choose? Again, let's calculate absolute time, right? So what we're going to do is, we still assume that the input size is 100. So what I will do is, let me use a different color here. So it's going to be 100 times 10 plus 3, right? You can see that's exactly this formula here, but with m being 100, right? And then if I'm using m1, that's going to be 2 multiplied by 2. All right? And of course, you can fill out this one here by yourself, okay, if you're interested. But I can already draw a conclusion. Let's now compare these two here. This is the absolute running time for algorithm number 1. This is the algorithm, so this is running time for algorithm number 2, the absolute. In order to determine which number is smaller, meaning that it's more efficient, do I really need to know what this is, either 2 or 4? Do I really need to know? Not really. I only need to compare this and this, because they will be multiplied by the same number. They can be factored out anyway. They can just be dropped. Agree? Very simple math inside here. All right, I'm going to put it here. So this second one here is even more interesting, I would say, inside here. So now compare this. So here, to compare the running time of 2 algorithm is not necessary to know the precise value of t, because t being equal to 2 or equal to 4, you will just get the same conclusion anyway, right? You only need to look at this part over here without this running time. Either it's 2 or it can be 4, doesn't really matter, right? You might just end up choosing, for example, let's say this one here, right? Because it's 7n, maybe. All right. Can be 2, can be 4. All right, not necessary. Okay, not necessary. The same conclusion can be drawn anyway. All right, any question about this table here? Right, this one just shows you some concrete, intuition about why absolute running time useful, but it may not be so necessary for thorough analysis. All right, so the conclusion is we can simply drop the t. We don't need to consider t anymore. Once we somehow know about the formula for figuring out the primitive operations involved in the algorithm, that should be enough for us to compare. We don't need to know exactly which execution platform we are dealing with. We should not. All right, that's good. Let's now go back here. All right, so this slide here, pretty much the same. The question here, just what I kind of explain, right? You can just look at that. All right, so this will be very important. The running time, that's the absolute running time, which would be the formula 7n minus 2, for example, multiplied by the precise number. But we said that it can be dropped. We don't need that, really. All right, and the rest, you can just take a look, just the same. So this will be the final thing we're going to carry forwards. To determine the time efficiency for an algorithm, or to compare that with an alternative competitor, we only focus on their number primitive operation. We don't need to worry about t. Okay. All right, any questions so far? Simple idea, but it's a very foundational idea to make sure you understand why we are making a transition. Robert?
Can we also drop like the constants?
Yeah, I'll get there. So the question was, let's say, for example, let's say this. Okay, well, Robert's question was like the following. If you look at this guy here, okay, this one here, and also this one here. Okay, this one, these two. We definitely can drop t. And when we actually try to compare, let's say, this formula here and this formula over here, we need another idea called the asymptotic analysis, meaning that when n gets to very large towards the limits, do we really have to worry about, for example, things like a 7 over here versus 10? It turns out we don't have to, right? That's another phase we got to discuss. But let's, one thing at a time. In this page here, we're just saying that we can drop t. Whether we can drop further information, we'll talk about it. Okay. All right, let's now move on. All right, so let's now try to approximate. Okay, let's see. All right, good. That's exactly what I'm talking about right now. Okay. So let's say if we got 7n minus 2. Let me go over a little bit bullet point, and then we'll do one exercise together. Let's say we got 7n minus 2, define max. And the way to really see that is like this, okay? Just to make sure you're comfortable with it. N here is like n to the power of 1, right? And 2 here is like a 2 times 1. And 1 itself is n to the power of 0. Okay, if you're having trouble with this math here, you got to speak to me, all right? It's very important, okay? Assuming that everybody's okay with this, okay? So let's say you got this formula over here. You basically got two terms over here. You got n to the power of 1. You also got n to the power of 0. We are going to say, whenever you want to somehow approximate the running time, you're just going to focus on the highest power. In this case, the highest power is n to the power of 1. And of course, the lower one will be n to the power of 0, right? This kind of relative, terms you want to talk about. We'll do another exercise, but let's just go over some terms. So we say n here to the power of 1 is the highest power. And then the 7 and 2 over here are called the multiplicative constants. And also the 2 over here, so think about there's only one, usually just one highest term. And then the remaining part will be may contain multiple lower terms. We'll see some example. All right, so when we try to approximate a function, right, and usually the function we're talking about really try to model the running time. We only focus on the highest power because asymptotically, the highest power is going to dominate the growth of the function, okay? And guys, by the way, today, unfortunately, it's going to be a little bit like a recap about what you learned from 1019 about the big O. Even though it's a prerequisite, but I think it might be nicer for us to go over that a little bit, just to see, just today. And then maybe a little bit on Thursday as well. And I'll make sure I kind of draw the connection from big O to coding, right? That's what the course is about. But for today, just be a little bit patient. We're going to go over some math. Okay, multiplicative constant and lower term can be dropped. Let's see one more example. Okay, but in the current example we are talking about, if you drop the lower term over here, the only thing you get left will be just n to the power of 1, right? So you can say we approximate 7n minus 2 as just n. All right, let's do one example here. Okay, together. All right, let's say this one here. How do we approximate this, right? I will also use this example here just to kind of recap about the terms that we have just learned on the slides. So I'll copy that. So this is the function you're going to get, right? This can well be the running time for some algorithm that you have designed. And let's now write it down one more time. So I got 7n plus 2n times log n plus 3n squared. All right, that's what's given. For this course, unless we say that explicitly, otherwise you can assume whenever we talk about log, it should be base 2. Okay. By default, base 2. All right, and then let's now rewrite this slightly, very slightly. So I can say 7 times n to the power of 1 plus 2 times n times log, if you like, I can put 2 here, plus 3 times n to the power of 2. All right, that's it, all right? Let's now try to review the terms that we spoke about. What is the highest power? 2 here, right? So now, one thing here. When you see n log n, This is something that you will also encounter quite often, especially when we talk about sorting algorithm. N log n is really a very efficient sorting algorithm, which we'll see later. But let's see n log n here. I want to give you some intuition here. We're not going to dive into too much math. So think about which one has a higher power, right? Roughly speaking. And of course, you can think about this is like a 1. And this one here is like a power is strictly less than 1. So what do I really mean power is strictly less than 1? That means the function here, mathematically speaking, as n goes bigger and bigger, this function here is going to grow more slowly than the linear function over here. Okay, that's what it means. But I'm going to draw you a diagram. Okay, let's put it aside. So if you have, let's say here. Okay, let's say you got here, you got here. All right. So let's say this one will be f of n, right? And this will be the n, which usually is the input size. Linear function, you know very well. Linear function is just like that. N. Linear. All right? This is to say f of n equals n. It's a bit like this. What about log n? It will look something like this. Maybe even a flatter, but you see the idea, right? So this one here is more like log base 2n. The idea would be, as n gets very, very, very large, you can see the gap between these two is going to be grow bigger and bigger. So we say that this one here has a lower power asymptotically than n. Right? So of course there will be many other functions which you have to also look into. There is a diagram coming very soon to summarize. Okay? But for now, we are only comparing n and also log 2n. All right? So based on this, you can think about what we have is, if you think about n log n, okay, just this part here, because we know that this one is 1, and this is about something less than 1. So we just got 1 point something, roughly speaking. Right? The power here is about 1 point something. The power is 1 point something, strictly less than 2. How about that? So that's why I didn't choose this one here as the highest power. It should be this one. That's really why I'm talking about that. All right, so let's now go over some terms. So number 1, so this guy over here is said to be the highest power. Okay, so let me just draw a little bit better. Okay, this one here is the highest power. And it is important to know that asymptotically, which I'm going to define in the slide coming very soon, asymptotically simply means towards the limits. This term dominates all the rest. Dominates over all the rest. Intuitively, if you want to observe the rate of growth of the running time of the whole thing, it will be enough just to observe how the highest power grow. All right, intuitively, only look at that will be enough, because that one there is going to dominate all the growth. All right, that's the highest power. So let me also highlight it here. And also, we got something called multiplicative constant. So you can see the 7 here, and also the 2 here, and also the 3 here. So these are the multiplicative constant. Multiplicative constants. And anything but the highest term will be the lower term. So you can think about here, let's say this. So the rest over here, just this part here, right? You know what? Let me just do a little bit better. This term here, this is one term, and this is just another term. These two are the lower terms. So this one here, and also this one here. So these are the lower terms. Lower term number 1 and lower term number 2, right? And that's the highest term. And to approximate this function here, that's really the thing we want to do. Number 1, you can drop all the lower term. Number 2, you can drop also the multiplicative constant for the highest term. So all we get will be, we can approximate this guy here as n squared. All right? That's how you approximate. All right? So the approximation, just n squared. And of course, you might be wondering, does that mean it will be big O of n squared? Yes. However, to really show that a function is a big O of n squared or something like that, you have to formally prove it. You might be asked to formally prove it, but we'll give you some methods to really solve that quickly as well, depending on how the question asks you. That's something we'll get into as well. But for now, we just understand, just to understand, if you want to approximate very quickly, you just focus on dropping the lower terms and drop the multiplicative constant for the highest term. So that's why we got n squared. All right. All right, guys, any questions so far? Pretty straightforward, huh? I hope. All right, that's good. And then, yeah, exactly what I just said, right? You can also refer to the slides. Okay, a few more slides, and then we can get to big O. All right, so given some, so we got f of n, like the number of primitive operation, right? 7n minus 2, again, something like that. So let's now go over some, okay, I think that this will be a nice way to really draw a little bit meaning conclusion up to now. So we talk about how you can figure out the running time, like a relative running time using f of n, which will give you the number of primitive operations. So now we just give you a spectrum of different functions there, and then we'll visualize them. So these are the most commonly seen functions in either here or maybe even in 3101. So don't really try to memorize them, but get a feel about why they should be that way, right? Okay, and we got something called, I will show you the diagram in just a moment. Let's see the bullet point. We got something called constant. We got something called logarithmic, log. Okay, and also we got linear, and also we got quadratic, power of 2. Also we got cubic, power of 3. And also we got exponential, 2 to the power of n. All right, so these are the common ones. There might be something I'm missing here, but good enough for now. Okay, let's now take a look at one quick visual summary over here. All right, I'll guide you through very quickly. The most ideal scenario for your algorithm's running time is constant, given that it's correct. So having a constant algorithm should not make you happy right away. You got to be correct, right? We talk about correctness, right? Assuming that it's correct. So constant is something that's so nice because let's now, so constant here is this function here, okay? Just at the bottom here, just about here. All right, constant. What does constant really mean? I want to talk about constant specifically. I think your fellow student usually have some confusion about why constant function is good, right? Okay, so now think about if I got some running time here. Let's say it's f of n equals, let's say 1,000, for example. 1,000 might look big to you, might, right? It's like a little bit like a 1,000 primitive operation will be involved. However, this one tells you it doesn't really matter how n might grow. It will always be 1,000 operation you have to execute. This one tells you, of course, when you got f of 1, what will be the relative running time? 1,000, constant. What about f of 100? It will also be 1,000. What about f of 1 million? Also 1,000. How about 1 billion? Also 1,000. So you can really see the advantage of a constant time algorithm when the input size gets very large. It can definitely just outperform all the others, right? So that's why you want to really get a true understanding about constant function there. All right? But for sophisticated problem, usually I would say it's hard to really get constant algorithm, right? when you have to, for example, you have to somehow involve certain complicated recursion or loops, you may not reach out to constant. But anyway, just understand the basic. Right, let's now go over very quickly. And the most expensive one is exponential. So it will be this one here. So this is the exponential function, which you would like to avoid as much as possible. However, sometimes it may not be that. It may be that you just have no choice. To really implement something correctly, you have to go with exponential, maybe. I wouldn't say there should be no scenario where you want to do exponential. Okay. All right, so anything else is actually in between, right? I'll just highlight a few more, okay? What about linear? Linear, I'm gonna use orange. Linear is this guy here. Think about linear over here. Okay, linear is here. I think, okay, so how about this? Sorry. Linear is triangle, yep. There we go. That's a linear. And then you can also see there's also the log that we spoke about earlier, right? The log would be something like this. Just growing slower, like that. Sorry. But you can see the correspondence a little bit more closely once you see the slides, right? Yeah, just remember the kind of the increasing order that we have, right? So just remember log algorithm will be considered as better than linear, okay? And the typical example we use to really talk about these two would be, so what you learn about just using a loop to go over maybe the database one by one. That's more like a linear algorithm. But later on, we're gonna see by using like a tree, you might be able to reduce back to log, right? That's something it's like one of the motivating examples we spoke about, but I'll get there later. Yeah, just look at this diagram more closely, right? Once you study that, okay? I'll leave that to you. All right. All right, just about the different kinds of running time that we can calculate. So there are three possibilities over here. So the way to understand this diagram is like this. Again, the vertical axis over here is about running time, okay, the vertical. And the horizontal axis over here is about different inputs you have, right? Different input, like a different test case. How about that? And the worst case, very straightforward. You just find the input that's going to trigger the highest running time, okay? And the best case will be the other extreme, which is just to find the input that's going to trigger the shortest or the smallest running time. And the average case time will be more like an expected value, right? Just average, like a mean. For this course, we are just going to focus more on the worst case running time, like a big O. That's what we will do, right? We definitely don't want to do best case because best case can be underestimating the running time for your algorithm. And for average case, I may not cover that in depth for some example in this course, but just bear in mind, average case may be the most accurate way to really kind of measure the running time, but it's going to require some analysis based on statistics or like a probability. So we may not touch that too much for this course. If I can ever talk about some example, I'll let you know. But for now, just remember this point. Right? We're going to focus more on the worst case running time. Right? If you know about what's going to be the worst case, at least you can get prepared, right? As the input gets large. All right. All right, asymptotic analysis. Okay. Let's go over some bullet points, and then we gotta also formally define the big O. Okay. Let me just go over maybe one more slide, and then we'll take a very short break, and then we'll resume. Okay. Okay, asymptotic analysis. And as I mentioned a few times, it's really about analyzing the behavior of your function, how the function grows towards the limits, infinity, really. So we are now even worry about maybe for small input size like a 100, 1,000, or even 1 million. We are really thinking about what about towards infinity, okay, towards the limits. Okay, so without a bound, right? That's what the kind of analysis we're doing. All right, so here, let's see, if you contrast over here, let's say here we got n squared, right? If you go back to the diagram over there, if you compare n and also n squared, you will see that n squared is going to grow much faster in terms of the input getting very big, right? And then I will revisit this maybe a little bit later when I talk about some property of the upper bound. Okay, just bear with me. For now, just to understand that what has the higher power. You can see n squared here has power 2, and n here has power 1. The higher power is going to be like a slower, right? It's going to take more time, basically. All right, so let's now do some very quick exercise, right? So now we want to be very familiar with the terminology, okay, about asymptotically, okay? Let's say here for the first one, all right, first one here. Let's say we got some running time here, we got some running time over here. And we know about how to approximate, right? For this one here, highest power is n squared, all right? So we can drop the lower term and drop the multiplicative constant. So we know that roughly speaking, it is n squared. We're just practicing what we learned earlier. And for this one here, also the highest term is n squared, right? Drop the lower terms and also drop the multiplicative constant for the highest term. This one here is also n squared, all right? You might be thinking before, 100 is pretty big, so that should be considered as like a less efficient. It will take more time than running time number 1. But asymptotically speaking, after approximating the function, they will be considered as equally efficient. Okay? So the conclusion we can draw over here is they are equally efficient. And it is important to add a context asymptotically. All right, that's good. Okay, let's do just one more. Okay, let's say we got these two running time. Okay, and the highest term for this one here should be just cube. By the way, you should not really expect the running time to be organized so nicely for you. You want to find out the highest power. For example, if I organize this one here as maybe 18 plus n cubed plus 7n, you don't really say, oh, I should always choose the first one. No, you want to choose the highest power, right? All right, so for this one here, the highest power should be n cubed. So drop the lower term, and the multiplicative constant here just 1, nothing to drop. Approximately n cubed. And the second one there, highest term, n to the power of 2. Drop the lower terms, and also drop the multiplicative constant here. So that will be n to the power of 2. So now we can make some meaningful comparison about the two running time. You can see here, they are both polynomial, but this one here has a strictly higher power than that. So we know that this guy here is more efficient because it's going to require less time to complete. All right. So here the conclusion will be, we're going to say running time number 2 is more efficient, meaning that taking less time asymptotically. All right, these two. All right, any question? All right, let's see if there's anything else on the slide before we reach the big O notation. All right, so for asymptotic bounds, that is something we're going to define formally, and then I'll tell you the story, maybe after the break, but let's see. So for this course, we're going to focus more on the big O. All right? And maybe in 3101, you guys will use more about omega, lower bound, and also tight bound, theta, right? That's something you might get into in 3101. But in this course, mainly big O. And I would suggest we take a very short break, and then after the break, we're going to get into big O mathematically. All right, so now let's get a little bit more mathematical. Okay, we're gonna talk about the definition for big O, which you guys might know already, but let's just review anyway. Okay. Also, I think it is important to not just to see the definition, but also to kind of visualize about how the definition can be understood. Because when you guys do some proofs, which I'll show to you, so I will give you quite a bit of example. So when you're given some, like a big O question, you may not be just asked to say, okay, determine what should be the big O family for this function here. I might ask you to somehow justify your answer, right? So let's do some a little bit more thorough. Maybe that can give you some different insight, right? So let's now go over some definition here, and then we'll visualize things quite a bit, okay? Okay, so let's say this, okay. I also need to do some a little bit additional thing. Good. All right, so usually when you see the definition, you will see two functions over here. You got f of n and g of n. I'll clarify them. But just remember the following. For both functions over here, the n here is more like a positive integer. The n here, think about normally just input size. So input size cannot be negative, right? So normally just 1 or 2 or 3, etc. And the output for both functions will just be some real number, like a running time, right? Running time. And then f of n, and okay, let me now just give you guys some quick reminder right away. Because when you see the definition, you will see both f and g. You don't want to get confused. Okay, let me write it here. Okay. So this page here is not yet a formal definition, just to kind of like a heads up. So what we have is we got f of n. All right, so this will be what we call the runtime function, running time function. What it does is, given the size of input, it's going to return the relative running time. For example, you might say f of n equals 7n minus 2, right? So f of n, just about the actual running time. And you will also see another function there, g of n. So this is what I call the reference function. Okay. So for this reference function here, you will expect certain manipulation on that. I'll just put it here. Okay. Further manipulation on g of n expected, usually. And the specific manipulation we are talking about here is change the slope of g of n. So for example, let's say here, manipulation here, given g of n, g of n, after some manipulation, I want to get c times g of n. And this one here is going to modify the slope of g of n. Okay, we'll see that, right? I'll just throw some reminders to you. Okay. All right, so what we really want to usually in the definition, as you will see, is the goal is for you guys to prove that f of n is the big O of g of n. That's something I will define formally. And visually speaking, it goes like this. Think about set, right? 1019, you learn about set, right? It's like a membership, kind of thing. When I say big O of g of n, it's like a family of functions. So I might say the big O of g of n. So think about g of n itself is just a reference. I'm using g of n to construct a family of functions, which is this set over here. And then I somehow want to show that or prove that f of n, my running time for the algorithm, is a member in the function. All right, that's what I normally want to do. So whenever you see people say f of n is big O of g of n, what does that really mean? It means that f of n is a member of the family of functions. And the family has been constructed by some reference function, which is called g of n. That's what you will see in the definition. So how exactly do we really say we want to construct such family? That's in the formal definition. We'll see. All right, just be clear about f of n versus g of n, right? That's going to be in the definition. Yeah, if you go back to the slides, you will see, okay, the big O of g of n is a family. And this is important. All the functions there, okay, I'll put it here. All the functions in this particular family here, if f of n being in the family means that it can somehow be, we call upper bounded by g of n. And of course, I haven't really spoken about what I really meant by upper bounded. We'll talk about it. And also, what do I really mean by somehow? Somehow is some process you have to come up with when you try to prove it, right? So somehow and also upper bounded is something you will see in the formal definition, right? So this page here just gives you some intuition about what's involved in the big O. All right, let's now move on. All right, so that's the definition, and I will go over with you one bits by bits. And this equation here is so-called upper bound effects for the big O, for the big O function. Okay, let's now go over the definition quickly, and then we'll see some example. Okay. All right. So this part here is the formal definition that you will see on the slides, which I show you very briefly. So we say that f of n, which is a runtime function. We say that it's a member. So you guys know this symbol, right? It's a membership, right? Good. So we say that f of n is a member of the family of function constructed based on g of n. So this corresponds to exactly this diagram over here. We can claim that f of n here is a member of the family here. You can say that if the following is shown. Okay, quickly. In order for you to prove, you got to find two things. Number one, you need to find some real constant, or can be integer, but real number is also possible. You want to find some constant c over here, and the c is the kind of manipulation you have to apply to g of n. Remember we talked about manipulation, right? To change the slope of g of n. That's number one. Number two, you also need to choose a size of the input. So we call n0. N0 is really the starting point where we're going to have the upper bound effects, like over here. Right, let me make some annotation. Okay. So these are the two things that you have to, okay, so let's do one by one. So the C here, start with that. This is the multiplicative constant. Apply to g of n. To change its slope. All right, that's a C. And then what about n0? Another thing you also have to choose is this one here, n0. All right. So this will be the starting points. Of the upper bound effects. All right, UBE, just an acronym, upper bound effects. I'll write it just once, right, just in case, right? upper bound effects. Right? And where exactly is the upper bound effects? Here. This is the upper bound effects. And the upper bound effects should really start happening from the input size being larger than or equal to the M0 you have chosen. Right? We'll see diagram in just one more. Let me recap very quickly. The definition tells you that whenever you're given a task to really show formally or prove that f of n is a member of the family constructed by g of n, two things. Number one, you got to choose the C. Number two, you got to choose n0. Once you have chosen these two, you have to show that this upper bound effect, which is like an inequality, is true for all the input size starting from n0. That's a formal definition. But let's now take a look at the diagram here. Okay? And this diagram here, I simply just got it from some textbook, which one of the reference textbook, from the syllabus. Somehow this diagram here only show the manipulated version of g of n already. It doesn't really show the original g of n, but it's okay. I'm going to show you that one in some concrete example, right? You can see here, I want you to look at in this way. So let's first of all start with here. If you can just, okay, let me see, what might be the best way. Okay, good. There we go. Look at this part over here. Just right here. All right. Let me do it slightly better. It should be strictly less than n0. There we go. Okay, that's the way to put it. All right, I want you to look at just this region of the function here. I'm basically trying to show the region that's strictly less than n0. When n is strictly less than n0. N is the input size, by the way. Input size over here is the n, right? You can see here when n is strictly less than n0, do we have the upper bound effects? That's a question, right? But you can see obviously this part over here is larger than this part, right? So this part over here is the g of n. Okay, so let's do it this way. So this is a runtime function. And this one over here is the manipulated version of the g of n, the reference function, right? You can see when n is strictly less than n0, f of n is actually not upper bounded by the manipulated version. It's not. If it was, then it should be, for example, this one, if that's upper bounded, the function should be up here, but it was not. All right, I'll write it down. The f of n is actually strictly larger than c times g of n. And it is important to know that this tells you that the upper bound effect is not there yet. Which is okay. Because in order to show that the big O is actually true, you only need to start at a certain point, which will be n0. All right, so that's the first portion. You want to make sure you understand why for this portion here, this equation is true, which tells you that upper bound effects is not the case. All right. And what about starting from n0? That looks much more promising. Starting from n0, you can see f of n is nicely bounded by something that's higher, which is c times g of n. That shows you that it can be nicely bounded. So that's why f of n should be a member of g of n, big O. Okay. Let's now just try to summarize that. So now if you look at starting from n0, let me use here. starting from n0 over here, for example, let me just do a little bit better. Starting from n0 over here. Okay. So that's what I can write. Starting from n equals n0, you can see here f of n is less than c times g of n. And that's exactly the upper bound effects. It's there. All right. And as you can see, the trends simply move on. There is not a point where you might get something like a cross and this one like that, right? If that happens, it's not really upper bound. Okay? Yeah. The trend just goes like that. So again, this one should nicely upper bounds the running time. And now we got to talk about more about how you can choose the C. Right? That's something we got to work on as well. All right, guys, any questions so far about the definition? Right? Spend some time, right? Just brushing up about what you learned from 1019, but this diagram here might give you a little bit more insights, excuse me, about understanding the definition. So what we'll do now, let's go over one more example, and I want to show you one more diagram, just to make sure it's completely obvious to you, and then we'll see how much exercise we can do. We've got about 15 minutes or so. All right, so let's now talk about this example here. So let's say we got the runtime function, 8n plus 5. And the reference function we have is just n. And somehow we want to prove that f of n, this guy here, is a member of the family of g of n, big O, right? That's something we want to do, okay? I want to show you one more terminology here, and then we'll come back to this example here. Okay, so if you can somehow show that f of n is in this, right? So there are different ways of saying that, okay? Either way is okay. You can either say, which I personally really prefer, this one really shows that it's a set, right? You can say f of n is a member of big O of g of n. That might be the most accurate way to really tell you there's a membership, right? We're checking. Sometimes people say, this might be the most common one. If you say f of n is big O of g of n, that one there in some ways not exactly making sense, strictly speaking. F of n here is like a member. You're saying a member is a family. You're comparing a member with a set, right? You cannot say that, but people say that anyway. But if you say that, it's okay. Just another way to say f of n is a member of big O of g of n. Or sometimes people say f of n is an order of g of n. That's also fine. Okay. Choose the one you like. All right, so let's now do this example here. Okay, we want to prove that an plus 5 is big O of n. All right, and then let's say here. So we're gonna somehow apply the definition. So for this first example here, since you guys just got brushed up about the definition, so I would just maybe expect you to do a little bit more, study maybe before Thursday. So for now, let's just walk you through the process quickly. Okay. We want to choose two things, as I said earlier, right? Just remind you quickly. We want to choose the C and also choose the N0, these two things, right? There is a proven strategy of choosing the C and also N0. We'll see if I'll at least tell you what that strategy is today, but we may also proving it is actually some useful exercise to do. I will see if I got enough time to do it. If no, definitely on the beginning on Thursday. But let's now go over this, right? Basically, you want to choose the C to change the slope of n. Think about g of n will be n, right? That's the reference function. And f of n will be an plus 5. We want to choose the C that's to be applied to the n, so we can change its slope. And that modifier will manipulate it, g of n, is going to upper bound an plus 5, starting from certain point n0, right? That's kind of the idea, right? And this will be the upper bound effects that we have. So this will be the f of n, and this g of n, this is g of n, and that's the chosen constant. Okay? So there are different ways you can choose it, right? So there are different ways to prove it as well. Right? Let's say we choose the following. Because I got 8 here, the multiplicative constant is 8. Why don't I choose just one larger than 8? Choose 9, let's say. Right? If I choose 9 over here, that's not enough. You still got to choose n0. What should n0 be? Guys, quick check about your kind of understanding, right? If I choose C to be 9, can I choose n0 to be 1? All right? That's a very important question here. Okay? Let me just go back there. I'll just show you this one very quickly, right? So we're given these two, and also we want to prove this. Let's say we have already chosen C to be 9. And before answering this question, let's say what about n0 is just 1? Okay? In order to see that, you have to plug in some number to see if the upper bound effect is really there. The upper bound effect, by definition, is this guy here, right? So what you want to do is function there f of 1, right? We'll talk about 1 here. Okay, so let me just highlight it. The 1 here, we want to make sure f of 1 is less than or equal to, and we choose C to be 9. 9 times g of n, which will be just n. And the n here is just 1, basically. All right? And, sorry, a little bit, you got to apply the number. What's f of 1? 13. 13 less than or equal to 9? Not the case. False. So we don't have upper bound effect just yet. That's something you kind of ask yourself to begin with. Okay? So no upper bound effects yet. If you can just calculate very quickly, what would be the smallest number for n0 where the upper bound effect is going to start happening? Go ahead. 5. Okay, pretty good. Okay. I'm pretty sure you have the same answer, right? Yeah. Okay, good. Okay. Okay, for the rest of you guys, if you're not too sure how to figure it out, I'll show you a table. Okay, you can work it out. All right, we did this one here and this one here because it is not the case that 13 is less than equal to 9. It's not the case, so not there. If you try 2, not yet. 21 is also not less than equal to 18. If you try 3, also not. Try 4, also not. But if you try 5, this is the very first value for n0 where the upper bound effects start happening. And to be sure, you may want to do just a few more just to make sure the trend will go on. You can see 53 also less than equal to 54, right? This is also some very important skill to really have because later on you will see that once we learn about the proof and strategy, of course you can apply that right away to save time. But there will be some edge cases where you have to check very carefully. I do have some example. Most likely on Thursday we'll talk about it. Yeah, make sure you also understand this table here. Okay, so we can choose C being equal to 9 and also 5, right? Not 1. All right, so now let's talk about the strategy. There is another way which I want to show to you. Somehow we can choose 13 and also 1. So why? So you guys exercise. Take a look at this particular combination of C and n0 and try to see if the upper bound effect can be happening right away. Okay, that will be your exercise. What I want to do now, I got about 8 minutes. Hopefully that'll be enough to do something a little bit mathematical, right? If I want to put you guys into sleep, write it now, rather than in the beginning of Thursday. Okay, I'll do it now. And this little proof is actually quite useful to really get some insights. Okay. Okay, so I'll get there. Okay, let's talk about this strategy over here. And this strategy here is saying, if you got some function running time like this, so it's more like a multiplicative constant. Let me just get to the formula right away. Okay. What we want to do is prove it. Okay, let me explain. Okay. Let's say your running time f of n looks like this. So assuming that it's being already sorted in terms of the lowest power all the way to the highest power. Okay? And then for each power there, you also have the corresponding multiplicative constant. Let's say A0, A1. So you can see the pattern here. To the power of 0, I got A0. To the power of 1, I got A1, etc. That's a general form for running time. All right? And then this one tells you that you can always prove that given this particular running time, the big O family should be D, the highest power. But how do you prove it? In order to prove it, to satisfy the formal definition, you need to choose the C and also N0. So here's the method. You can always get N0 being equal to 1 if you choose the C being the sum of the absolute values for all the multiplicative constant. You basically want to take A0, A1 all the way to AD and take their absolute value and add them up together. All right? So I got 7 minutes. Let's do quickly the proof. And I want you guys to really somehow see the proof, and then we can get back to the rest next time. Okay? Let's see this. So the proof contains actually 2 steps. Number 1, you want to make sure N0 is going to be, so since I say N0 should be 1, I want to argue that start at 1 specifically, upper bound effect is there. And also for any other values of N that's larger than 1 is also there, basically, right? So you can think about, I'm going to divide the proofs into 2 steps over here. So step number 1, I want to make sure f of 1, right, you can see N is already being substituted by 1, should be upper bounded by, so the C here is the C here, right? I'm just not repeating the C here, multiplied by the highest power. Because I say, you can think about this one here, this is like a G of N. Okay, so let me just put this in red. This guy here is the G of N. Okay, I want to make sure it's G of N is N to the power of D. N to the power of D. And in this particular case, the N here is just 1, right? Just the input 1. That's number 1 I want to show. Number 2, the more general case, I want to show that the f of N should be less than or equal to C times N to the power of D. And here, I'm assuming that N is larger than 1. I want to prove this one and show this one as well. All right, these 2. Okay, let's at least do 1. So now how do I show this, right? You can see this part here exactly, so it kind of expands C. C here is this one here, which is here. All right, how do I show that? Let's do this one at least. So I got here f of 1. And then why don't we simply replace this N here just by 1 and see what's going to happen, right? So N here will be 1, and also N here will be 1, etc. I got A0 times 1 to the power of 0 plus A1 multiplied by 1 to the power of 1 plus all the way to A D multiplied by 1 to the power of D. All right? And I'm going to do some simplification over here, and then I'll put some justification here as well in a moment. I'm claiming that this particular term can be simplified into the following. It can be simplified into, I'm taking this one, all the multiplicative constant. A0 plus A1 plus all the way to AD. Right? And then I'm going to get over here N to the power of 1 to the power of D. Beg your pardon. 1 to the power of D. And the reason that I can do this is because so I put star here. Let me put a star here. Okay. I know pretty well 1 to the power 0 equals 1 to the power of 1 equals all the way to 1 to the power of d. They are simply just 1. 1 to the power of anything is just 1. All right. And let's conclude this case. Okay. So this one here, I can say this one here should be less than or equal to A0 plus A1 plus all the way to AD. And then times 1 to the power of d. And this one here should also be very obvious to see. For example, if you look at A0 here and A0 here, it is for sure A0 should be less than or equal to its absolute value. And also A1 here should also be less than or equal to its absolute value, right? And etc. That's why this inequality here will also hold. I'll put it down as well. Okay, so now star number 2. So I know that A0 is less than or equal to its absolute value. A1 here is also less than or equal to its absolute value, and etc. All right, that's how I argue about the first case over here. The math itself, I understand, it's pretty basic and kind of tedious, but it does give us some idea about how you're supposed to apply different cases for upper bound effects. All right, so give it a try very quickly. Maybe on this one here, I'm going to go over this part here on Thursday, right? Okay, we're good. I'm going to finish the mathematical part, and then we're going to go over lots of examples on Thursday. Okay, see you then.